One of the first experiments which we will do is to learn about solubility in organic chemistry. And this is to accompany experiments 1, parts A, C, and D, which comes out of the Small Scale Approach to Organic Chemistry book. So we will be following through a little bit of the pre-lab lecture for those experiments. Now, solubility in organic chemistry is a little bit different from what we might remember from general chemistry. If you remember, in general chemistry, at least, we had a set of rules for ionic compounds. And remember, when I'm talking about ionic compounds, another term is salts, right? An ion pair, a positive and negative compound together. We had rules in general chemistry, at least, about ionic compounds and how they dissolved in aqueous solutions. Now, we shouldn't forget any of those rules, or I'm not to say that those aren't important within organic chemistry, but there's a little bit different approach that we have to take while we're in the realm of organic chemistry, and that's what we want to talk about. It's going to be extremely important for us to kind of be able to predict solubility when a liquid is soluble in another liquid, or when a solid is soluble in a liquid. Both of those are going to be extremely important. Now the question is, right, as with most of the topics which we discuss, why do we care, right? So why do we care about solubility? Why do we need to know about solubility to begin with? Well, we got to think here for just a second. Okay, so most of the experiments that we're doing within the lab this semester, we're going to take some kind of solid, right, our starting material, and we want to react that. We want to do some reaction, right, some reaction to get a product. And our product is typically a solid too. So we start with some solid starting material, we do a reaction, we want to get a product out of it. Now the problem is this: if we begin as a solid, how are we going to react that? Because remember, for a reaction to happen, molecules have to combine together in specific ways, right? One atom has to hit another atom, or one molecule has to hit another atom in a very specific way. They have to be moving around so that orbitals overlap and that the reaction can proceed to make our product. But think about this: if I just have a lump of salt, and table salt, and I put it on a countertop, what's going to happen to it? The answer for the most part is nothing, right? The salt's not really going to react with anything. And so what we have to do is we have to take this solid here, our starting material, and we have to put that into solution. So we have to dissolve it in something, and then our reaction can proceed and we can get our product out of it. So the big thing that we need to think about is, how does solubility affect what we can do in the lab? The majority of the experiments which we're going to be conducting are going to be in the solution phase, whether it's aqueous or, for the most part, in organic at least, it's going to be in some kind of organic solvent. So we have to know our solubility of our compound so that we can make a solution out of it, so that we can proceed and make our proceed with our reaction. So how can we start to look at solubility or predict solubility? Well, there's a couple of things that go into it, but one of the main topics, or the main ideas that we need to remember, is this intermolecular forces. And if you recall from general chemistry, there are 3 of these intermolecular forces. There's dispersion, there's dipole-dipole, and there's hydrogen bonding. Now, a dispersion force is also known as a London or a van der Waals. These are intermolecular forces that are present in any molecule. But let's think here for just a second. What is an intermolecular force? Right, so an intermolecular force just means how molecules talk to each other. They are intermolecular, right, between one molecule and another. Just like an interstate highway goes from one state to another. It connects them. That's the way that these states communicate, so to speak. That's how traffic gets across to each other with an interstate highway. So an intermolecular force is just how different molecules talk to each other. Okay, so dispersion forces. Dispersion forces, let's define it. Let's call it a temporary. So a temporary separation of partial charges. Whoops. Would help if I spell, right, partial charges. Okie dokie. So temporary separation of partial charges. Let's underline some important things here, right? So temporary and partial, okay? So every known molecule that we've observed so far has dispersion forces. That's because dispersion forces come from the electron clouds. Remember, electrons are a huge driving force behind how molecules react and their properties and all these things. So it's because of how the electrons are that we can have dispersion forces. Let's take a look at a quick example. So if we look at our molecule I2, iodine, right, elemental iodine. If I draw my Lewis structure for this, okay, so let's draw a Lewis structure. There's one iodine molecule. Let's just make it a little bit neater. One iodine molecule, another iodine molecule, and fill in my lone pairs. Good. So there's all that stuff, right? What do we see about this molecule itself? And we say, well, it looks pretty symmetrical, it's linear, right? Everything's got the lone pairs in there. We can just talk about octet rules and all that kind of stuff. And that's all fine. But now we got to think about it. What is actually happening here? So we have one iodine molecule, right? We got this guy here bound to another iodine molecule, that guy there. Now, if you recall, right, there's something always at work behind the scenes when molecules bond to each other. There's always a tug of war between the electrons. There's a tug of war between the negative electrons being attracted to the positive nuclei of whatever atom they're bound to, right? And so we have to think, all right, which one of these iodines, one or two, is winning that tug of war? Is one of these iodines stronger at pulling electrons than the other one is? And the answer is no, right? They're both iodine molecules. They're of equal strength, right? They've both been going to the gym for the same amount of time. One of them can't lift weights more than the other, so there's an equal pull. That means they're sharing electrons, right? We have a covalent bond. Let's call it a non-polar covalent bond, if you remember that terminology. So then how can we get partial charges here? Well, what happens is, remember we're dealing with intermolecular forces, so let's bring in another iodine molecule. Okay, so let's start to bring in another iodine molecule, and we'll call this 3 and 4. All right. So as we start to bring these two iodine molecules together, the first thing that's going to happen is that these electrons, right, our lone pairs that we have seen there, are going to start to interact with the other electrons on the other iodine molecule. So let's think that, you know, right in between here, right, in those blue lines, those electrons are going to start to interact with each other. So what does that mean? Okay, well, we have negative electrons on iodine number 2 interacting with negative electrons on iodine number 3. So what's going to happen? Two negative things are going to repel each other. And so if let's draw a blue line here to indicate what happens after that repulsion. So after that repulsion, there's my two iodine molecules, okay? Let's say that the electrons on 3 get repulsed, okay? So they're pushed away. I'm going to represent my electrons as a cloud now, right? So let's say that on iodine number 3 here, right, the electrons get pushed away from iodine number 2. Remember, I'm just representing the clouds of electrons rather than the lone pairs themselves. Okay, so taking a look at the cloud of electrons that I've drawn there, that means that iodine number 4 now has a larger cloud of electrons around it. So it has more electron density around it. So what does that mean then? If I've got more electron density around me, how is iodine number 4 feeling? Well, it's feeling partially negative, right? It's got more electrons around there. If that iodine is feeling partially negative, iodine number 3 then has to feel partially positive. Aha! So we've started and we've made a temporary separation of charges. But remember, we're dealing with the intermolecular forces. So we repulsed the electrons away and we generated a partial separation of charges. But now take a look at iodine 2 and iodine 3. Iodine 3 is feeling positive. So what's going to happen to the electrons around iodine 2? Well, they're going to get attracted to that partial charge on iodine number 3. And so the electrons are going to start to swarm around iodine 2 a little bit more to get that negative positive interaction here between those molecules. Now, if iodine 2 feels partially negative, then iodine 1 feels partially positive. And we could continue to draw more and more iodine atoms. So what happens, to summarize this, right, what happens in a dispersion force is when two molecules come together, the electron clouds can repulse each other, right, they can repel each other, and that causes these temporary formation of negative and positive charges. Now, dispersion forces can either be the weakest or the strongest force. And that's a pretty vague statement, right? It can either be very weak or very strong. Very helpful. Thank you, Dr. Hillesheim. Here's what I mean. It's solely based off of how many electrons you guys have. The more electrons a molecule has, you can have massive dispersion forces. So if you think of something like your DNA, where you've got hundreds of thousands of electrons around, you can make some pretty significant dispersion forces that form. But in something, let's say like hydrogen, H2, right? In something like H2, there's only 2 electrons around. Your dispersion forces are going to be pretty weak. So remember, with dispersion forces, it's all based off of how many electrons. The more electrons you have, the bigger the forces, the stronger it can be. Okay, now a dipole, okay, let's move along here down to the next topic of dipoles. Now a dipole is very similar to a dispersion force, except that it is a permanent. So a permanent separation of partial charges. So a permanent separation of partial charges. So now we have to go back and think about our tug of war again. Let's take a look at a typical organic molecule. Let's take a look at something called acetone. So here's our buddy acetone. We can draw this a little bit more in depth. There's our carbon, 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 right? We'll just do CH3, CH3, and a double bond to an oxygen here. Okay. And we say, that's a very nice ketone there, right? Everything's obeying the octet, looks nice, carbons and hydrogens and all that kind of stuff. What intermolecular forces can be present in something like acetone? Well, here we have to remember to look at how well things are playing tug of war. Now remember, when I'm talking about tug of war, I'm talking about electronegativity. Okay? Quote, tug of war. All right. So remember, atoms are always going to be pulling electrons, or going to be trying to pull electrons towards themselves. But some atoms have been going to the gym a little bit more, right? They got their CrossFit membership there for Christmas, and so they are trying to win the tug of war and pull more electrons towards themselves. Now, it's extremely helpful for you guys to know your top 4. I want to take a little bit of an aside here. So our top 4 most electronegative atoms. Okay. Fluorine's your most electronegative, followed by oxygen, followed by nitrogen, which is approximately equal to chlorine. Okay. Nitrogen has a slight lead on the electronegativity of chlorine, although it does depend on what textbook you're looking at and these kind of things. So it is a little bit wonky there, but we'll go with this order for now, right? So fluorine, oxygen, nitrogen, and chlorine. So the more electronegative an atom is, the more it can pull electrons towards itself. So let's go back to our buddy acetone. What is the most electronegative atom in acetone? Well, knowing our top 4 electronegative atoms, there's our oxygen right here, right? There's our oxygen right there. I'm just going to put a little red box around it for the moment, okay? That is the most electronegative atom. So it's going to be pulling electrons towards itself. Well, where is it pulling electrons from? Well, you can only pull electrons from what you're bound to, okay? So that oxygen is only bound to that carbon atom. So it's going to be pulling electrons from that carbon. If it pulls electrons from that carbon, that means the oxygen itself is negative and that carbon is positive. Now that's a permanent separation, right? Electronegativity isn't going to change, right, from one day to another, okay? So that negative and positive is permanent. So one acetone atom is always going to have a negative and positive end, and that negative and positive can interact with another acetone atom, and so on and so on. So similar to what happened in dispersion, the negative and positive ends of molecules can interact with each other. Now hydrogen bonding, okay, moving on to the last topic here for this slide. Hydrogen bonding is, let's call it a special case of dipoles. Okay, let's use our buddy ethanol in this case. So here is ethanol. All right, now hydrogen bonding happens when a hydrogen atom is bound to three specific atoms. So when hydrogen is bound specifically to fluorine, oxygen, or nitrogen, we can have hydrogen bonding occur. Now, giving you guys a big hint, right? So when hydrogen is bound to fluorine, oxygen, or nitrogen, we can see hydrogen bonding form. And we go, that's interesting. What do we know about fluorine, oxygen, and nitrogen? Well, they are three of the most electronegative atoms that we have, which means that in our ethanol molecule here, that oxygen is feeling particularly negative. It's really pulling electrons away from all the other atoms. Now, hydrogen itself really can't pull anything. Okay, it's not a very electronegative atom. So it's going to be feeling pretty partially positive. And so here we see our separation of negative and positive, and it is a very, very, very strong intermolecular force, hydrogen bonding. It can make it's easy for hydrogen bonding to form or form very strong intermolecular forces. And so let's just draw in another ethanol molecule here just to kind of show what's going on. So we got the partial positive here, partial negative here, right? And we got that interaction between the negative and the positive ends between the two ethanol molecules. So to summarize this real quick, there are three intermolecular forces. They are based off of electronegativity, and they have to deal with the separation of partial charges. Now, why is this relevant to solubility? Well, the more you have in common, so the more you share with intermolecular forces, the better your molecules can talk to each other, the more likely they are to be soluble. So where you start with predicting solubility would be to look at the molecule that you have and take a look at intermolecular forces and take a look at the structure of it. Take a look at the formula, take a look at the atoms that are present, right? And take a look at where charges are. The more you can communicate between your solvent and whatever you're trying to dissolve, the more likely it is that they're going to be soluble in each other. So as we talked about on the previous slides, we need to know about solubility for a couple of different reasons. And we discussed that, one of the big reasons that we need to know is to be able to predict which of our compounds are going to be soluble in what solvents. And so with that idea, we were discussing the concept of solids dissolving into liquids to make a solution. But we can't forget about liquids dissolving in other liquids. Again, when we're talking about the solubility of liquids, we go back to this idea of intermolecular forces to kind of help us predict. It should be noted that intermolecular forces are not the only concept that are used when dealing with the solubility. We also need to remember the actual structure of the compound itself. So we need to know the geometry of the molecule and know about whether it has an overall molecular dipole or not. That's a very important topic. And so if that's not familiar with you, go back and check through your old notes about dipoles and molecular geometry. These are very important topics when dealing with solubility that go in conjunction with intermolecular forces also. So let's talk real quick about miscible and immiscible liquids. Now, miscible and immiscible liquids just means, does one liquid make a solution with the other, or do we have a layer? So the quintessential example, I would say, with an immiscible liquid is oil, and water, where if you try and put oil and water together, you can shake them up, you can stir them, blend them, whatever it is, and they're eventually going to just separate out to where oil's on top and water's on bottom. And I believe if I clean this up for just a bit here, I have a picture of that for you. So here it is, okay? So let's take a look at what's going on in these two pictures here. So first of all, let's talk about what it is that we're showing here. So this, right, I'm just outlining this piece of glass right here. So what I'm highlighting there in green, that's what's known as a separatory funnel. So a separatory funnel. Now, a separatory funnel in organic chemistry is used to separate liquids from each other. So if you take a look in the nice picture that we have here, right, we've got three layers that are clearly shown in the three colors, the red, the clear, and the blue there, or the red, white, and blue maybe, although it looks like a clear liquid. So these three liquids are immiscible. They form three distinct layers, right? They are not mixing with each other to make one homogeneous liquid. Now, what can we say just by looking at this picture? Right, we have the red, the clear, and the blue liquids there. Well, what we can really talk about is the density of those three liquids. So which of those three liquids is the most dense, right? Or the heaviest, right? The heaviest or the most dense, if you want to think about it like that. So the density of a liquid is going to be important also. When we're using a separatory funnel in the lab, and we will be using them quite a bit, you need to remember what the density of these liquids are. Now, the blue liquid in this case is going to be the most dense, right? It's going to be on the bottom. And then the white has the second highest density, and the red is the least dense of the liquids in that picture. Now, with respect to organic solvents, typically organic solvents have low densities. So organic solvents, they typically have low densities. And of course, your first question should be, well, what is the word low is relative, right? Relative to what? Low densities compared to water. Now, we just assume, for all intents and purposes, that water is going to have a density of 1 gram per milliliter, and our typical organic solvents have densities that are less than 1. That means when we're using a separatory funnel, water is usually going to be the lower, right? Water is usually going to be the lower layer in our sep funnel, and then our organic solvent is going to be on top. There are a couple exceptions to this, but that's why it's extremely important for you to go through your pre-labs, so that you have your densities for the solvents and everything that you're using, so that you know where in your separatory funnel to look for your organic versus your aqueous layer. All right, let's clean this up here a little bit. Now, even with the best of knowledge with intermolecular forces and densities and the structures and the dipoles, there are some oddities when it comes to determining miscible versus immiscible liquids. And so that's why we are doing some science, right? There are some oddities, right? And what I mean by oddities, there are some things that may not exactly follow the rules that we have predicted. And that's okay, because that's where we do some science to figure it out, right? So in part C of the lab that you're doing today, you're going to be going through and checking whether some of these whether some of the liquids that you're using are going to be miscible or immiscible. So use your intermolecular forces, think about the structure of these, and predict what do you think is going to happen before you even get into the lab. And then if you see something that goes against your predictions, then we can stop and say, okay, well, can we explain what's going on with this? So we're going to do a little bit of science to figure out whether some liquids and solvents are miscible or immiscible. So in the last part of today's lab, you're going to be looking at the solubility of acids and bases. Now we have to remember what we're talking about with acids and bases. And there are two definitions which are used most commonly. The first one is a Bronsted acid and base, and that's probably the most common use of the term acid and base. So real quick, remember a Bronsted acid is a proton donor, so an H+ donor. And a Bronsted base is a proton acceptor. Now, I can't emphasize enough how important it is to know about acids and bases. If you remember from your first semester of organic, how many of our reactions are either catalyzed by acids, or they're promoted by acids, or the mechanisms at place are, have acids and bases involved. It is very, 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 very important to understand acids and bases. And so most commonly here we're dealing with Bronsted acids and bases. And you say, okay, again, why do we need to know about the solubility of these? Remember, when we're doing a reaction, right, we have to get everything into solution, or we have to separate things out, or we need to get things dissolved, right? So organic acids and bases need to be dissolved in solution before they can go through and catalyze or do the reaction that we want them to. The other definition that we might run into is this idea of a Lewis acid and base, where here, with a Lewis acid, we have a lone pair acceptor, and a base is a lone pair donor. Okay. So Lewis acids and bases are far more prevalent in the second semester of organic chemistry. So you will see a lot of Lewis acid-base chemistry happen there. Let's go back and talk a little bit more about the Bronsted acids and bases, though. So probably the most common example of a Bronsted acid, at least from an organic acid, is when you have a carboxylic acid. Remember, a carboxylic acid looks something like this, right? Where we have two oxygens and one of them is bound to a hydrogen. I'm going to start to color code a little bit of the important stuff here. So this hydrogen at the end there in purple, that is your acidic hydrogen. And so we go back to the overarching question of this lecture and say, okay, is this is this benzoic acid, which is what this is called, benzoic acid, is benzoic acid soluble in water? And we would take a look at the molecule, say, well, there's a lot of carbons and hydrogens. It's not very polar. There's only one end of it which is polar, but it's got a lot of non-polar ends. So I would predict that benzoic acid is not soluble in water. You say, well, it can hydrogen bond. You're right, but the majority of the molecule is not very polar. And so we'd say this is not soluble in water, and that's true. You say, okay, well, I need to get benzoic acid into solution. What can I do? Well, here's where we can use some science. So let's take benzoic acid and let's react benzoic acid with sodium hydroxide. And let's put sodium hydroxide in, let's draw it in green over here. So there's my hydroxide, right? The sodium we're not really going to worry about, right? It's a spectator ion. And let's do this in water. Now, what's going to happen if we put an aqueous solution of sodium hydroxide with benzoic acid? Well, sodium hydroxide is a base, right? This is a base. So what happens when we mix a base and an acid? Well, we can draw some mechanism arrows, right? The base goes to grab a hydrogen, right? Now, if we follow our arrows there, we end up forming this guy. And let me get some colors in here, right? There's a lone pair. Sounds good. Here's our hydroxide, right? That forms a bond with the originally purple hydrogen there, okay? And so take a quick second, follow the mechanism arrows and the color coding that I did in there. All right, so now what happened? Well, here we have benzoate ion and our good old buddy water. Okay. So if we do an acid-base reaction with benzoic acid and sodium hydroxide, we end up forming a benzoate ion and water. Let's look at this guy right here. Now what can we say about this? Well, we formed an ion, right? We formed a charged molecule, a negatively charged molecule. Generally speaking, ions are far more soluble in water than neutral compounds are. So even though we still have the majority of this compound as nonpolar, right? And remember, what I'm looking at for nonpolar is this end right here, right? That's a nonpolar end, okay? Only carbons and hydrogens there, so that's not very soluble in water, but because this is ionic, right? Because we have a negative charge, so sodium benzoate or a benzoate ion is going to be water soluble, okay? So typically speaking, ions are more soluble in water than neutral compounds are. Now the question is, I want to get benzoic acid back out of water. How can I turn benzoate into benzoic acid? AKA, how can I go back? How can I go in reverse? And that's a question we're going to answer in lab when you guys get there. So in summary, for organic acids and bases, don't forget your definitions. Acids are proton donors, bases are proton acceptors. Ionic compounds tend to be more soluble in water than neutral compounds are. And the most common acids that we tend to see in terms of organic acids are these carboxylic acids.